All right, let's dive straight into what is absolutely the ultimate cosmic detective story. Welcome to this explainer. Today, we're searching for an ancient signal that has been traveling towards us since the literal dawn of time. We're talking about the Cosmic Neutrino Background, or the C-nu-B for short. Now, it's a fundamental prediction of our standard model of cosmology, and yet it remains one of the single most elusive targets in all of modern physics.
Just imagine trying to intercept a transmission that was broadcast nearly 14 billion years ago. We are talking about a message that is silently passing right through your body, through the room you're sitting in, and through your screen at this very exact moment. To unlock the secrets of the early universe, we have to catch these relics. But to do that, we first need to know what exactly we're looking for.
So to decode this ancient message, we first got to meet our elusive suspect, the neutrino. You've probably heard them called the ghost particles of the universe, and for good reason. A neutrino is an incredibly standoffish elementary particle. It has no electrical charge and an infinitesimally small mass, and because it only interacts via gravity and the weak subatomic force, it basically ignores almost all normal matter. I mean, you could put a block of lead a light year thick in front of a neutrino, and it would likely just breeze right through it without a second thought.
The sheer scale of what we're dealing with here is just staggering. Even though they're virtually undetectable, there's an average of 336 of these specific cosmic relics in every single cubic centimeter of space today. Picture a tiny cube, maybe the size of a sugar cube. There are over 300 of these ancient particles sitting inside it right now. Wild, right?
And because they're packed so densely throughout the cosmos, the neutrino is literally the second most abundant particle in the entire universe. As our source material points out, the only things that outnumber these ghostly remnants of creation are the photons from the cosmic microwave background. Everything else, all the electrons, protons, and neutrons that make up the stars, the planets, and us, it's all just a tiny rounding error by comparison.
Let's put this into perspective on a cosmic timeline to see just how ancient these particles are. We constantly hear about the cosmic microwave background, right? That afterglow of the Big Bang release 380,000 years after the universe began. But look at how incredibly early the neutrinos broke free. These particles were released into the universe just 1 second after the Big Bang. 1 single second. That is a massive leap back in time.
This maps out what we call the Great Decoupling. During that literal first second of cosmic time, the universe was this rapidly expanding, unimaginably hot plasma of photons, electrons, and neutrinos. They were all smashing into each other, constantly keeping things in thermal equilibrium. But as the universe expanded, it naturally cooled. Once the temperature dropped to about 10 billion degrees Kelvin, which is roughly 1 mega-electron volt, the universe was simply expanding too fast for the weak interactions to keep up. The plasma just became way too sparse and cold for the neutrinos to keep bouncing off the other particles.
So here's the absolutely crucial takeaway. The very moment the decoupling happened, these specific neutrinos basically stopped interacting with the rest of the universe. They have been flying untouched, coasting as completely free agents ever since the universe was a single second old. They're in a state scientists call free streaming, meaning they are carrying a pristine, totally unaltered snapshot of the very early universe.
When you compare our two cosmic echoes side by side, you can easily see why the neutrino background is both so much older and significantly colder than the microwave background we already map. The CMB photons are sitting at about 2.7 Kelvin today. But the cosmic neutrino background? It's even colder, way down at roughly 1.95 Kelvin.
What's really fascinating here is seeing how these free-streaming neutrinos traveled right alongside those photons. In the early universe, way before stars or galaxies even existed, neutrinos made up a massive 41% of the total radiation energy density. And the sheer gravitational weight of all those ghost particles left massive imprints on how early galaxies formed, which, by the way, is the primary indirect evidence we have today that they actually exist, even though we haven't directly caught one yet.
But today, after billions of years of the universe stretching out, the energy of these particles has been spread incredibly thin. Like we saw, the temperature of this neutrino background has plummeted to a freezing 1.95 Kelvin. For some real-world context, that is about minus 271 degrees Celsius. It is barely above absolute zero. Now you might be wondering, wait, why is the younger cosmic microwave background actually hotter than the older neutrino background? It's a great question, and it all comes down to cosmic timing. Shortly after the neutrinos decoupled and went their own way, the universe cooled just enough that electrons and positrons started annihilating each other en masse.
This huge annihilation dumped all of their heat and entropy directly into the photons. That permanently boosted the temperature of the CMB while leaving our ghostly, free-streaming neutrinos completely out in the cold.
Which brings us to the ultimate catch-22. If there are literally hundreds of these relic neutrinos floating through a space the size of a sugar cube every single second, why haven't we caught even one? How on earth do you trap a frozen ghost that fundamentally refuses to interact with normal matter?
Well, the experimental challenge we face is just staggering. Our conventional neutrino detectors, those massive underground tanks of liquid we currently use, they need incoming neutrinos to have a baseline energy of around 300 kiloelectron volts just to trigger a reaction. But our ancient cosmic relics, they've been totally sapped of their energy by the expanding universe, sitting at a microscopic kinetic energy of roughly 0.17 millielectron volts. They're incredibly slow, their momentum is practically gone, and their energy is literally 1 billion times too low for standard detectors to even notice.
But hey, physicists love a challenge. Scientists are engineering some really cutting-edge traps to get around this exact energy problem. A major proposal right now is the PTOMY experiment. Instead of waiting for a neutrino to smash into a target with high energy, PTOMY plans to use a radioactive isotope called tritium. Because tritium is already unstable and actually wants to decay, capturing a neutrino becomes an exothermic process. That means it doesn't require a minimum threshold of energy from the incoming neutrino to happen. The detector will simply look for the tiny, hyper-precise energy bump that a captured cosmic neutrino would leave behind on an emitted electron.
And we actually have a bit of a cosmic wildcard playing in our favor here. Because these ancient particles have lost so much kinetic energy over 14 billion years, they are moving so slowly today. And because they're basically crawling along, the massive gravitational pull of our Milky Way galaxy and nearby galaxy clusters might actually be trapping them. This gravitational clustering means that the local density of these relic neutrinos right here on Earth could be significantly higher than the cosmic average. That gives our experiments a much better chance at a catch.
So, why go through all this trouble? Well, successfully capturing this background wouldn't just be a neat experimental trick. It would completely revolutionize physics. A direct detection gives us the absolute, definitive proof of our standard Big Bang cosmology. Plus, because they are so low energy, catching them could finally reveal the exact, absolute mass of the neutrino. It might even solve a decades-old mystery by showing whether neutrinos are their own antiparticles, a concept known as Mariana particles. And on top of all that, it could give us our very first real window into the invisible dark sector of the universe. For decades, the cosmic microwave background has been the absolute limit of what we could see, a literal wall of light from 380,000 years after the Big Bang. But the cosmic neutrino background? That is the ultimate prize. It's a tool that allows us to bypass that glowing plasma and stare directly into the literal first second of the universe's creation.
Which leaves us with one incredibly thrilling thought to ponder today. As our technology finally starts catching up to our cosmological theories, we are getting agonizingly close to intercepting the oldest message ever broadcast. And if we can finally decode a ghost that has been flying silently through space for 14 billion years, what else is waiting for us out there in the dark?